All right, so electricity. That's the first topic we'll look at. So we'll do electricity. That'll be homeworks 1 through 4. Basically, your exam 1 is electricity. Then we'll move into magnetism and then combine them into electromagnetism. That's homeworks 5 through 7. That's your second exam. And then we'll move on to light, optics, and so forth. And hopefully have a little bit of time for modern or quantum physics at the end. But the big units in this class are electricity and magnetism. So first topic, electric force. So right away, force. You recognize an old friend from physics 1. So all of the things that you can do with forces, you can do here. You have Newton's laws, right? Good old Newton's laws. The cornerstone of which, of course, is F net equals ma. So if you apply a net force on an object, it will accelerate or change its motion. How much? Well, it depends on how inherently stubborn it is to that change. That's what we measure with mass. We have other things like Newton's third law, which is that the forces that are of two objects interacting are equal and opposite. So these all should be familiar things. And of course, one of the major things we did in physics 1 is net force is just net or overall force, how much force acts on an object and in what direction. And then there are lots of different things from the outside world that can be forces. So here's a list, a hopefully semi-complete list of physics 1. Force of gravity, also known as weight. We have tension, that's the force from a rope or a string. We have the normal force. That's the force from a solid surface that makes sure it doesn't get smashed. We have the force of friction. We have the spring force. We have buoyant force. I think that's pretty much a complete list from physics 1. I didn't put in centripetal because doesn't belong in this category of real world forces, and you should know why. So the thing I want to point out, did I forget any others? Is there anything else in physics 1? I think that should be a pretty good list. So the thing I want to point out is that all of these here, with the exception of gravity, are really just kind of ad hoc manifestations of the same force, electric force. So if you look at that list, they all depend on in some way on atomic cohesion, right? Tension, a rope doesn't want to break because of its chemical bonds, right? A normal force, a surface doesn't want to get smushed because it wants to stay together, so on and so forth. They all depend on atoms staying together and atoms staying together with other atoms and molecules. So they're really, we'll find what's responsible for that is electric force. The only one that is not that is gravity. So there's really, these are two of the fundamental forces of the universe. There's gravity, there's electromagnetism. We'll find that we can combine all that stuff. Electricity and magnetism can go into one. Then there's a strong nuclear force and a weak nuclear force, and that's it. Okay, 4 fundamental forces of the universe. Weak force we won't talk about at all. Strong nuclear force I'll mention briefly in passing at some point. Force of gravity we discussed extensively in physics 1, and so our mission right now is to fill in the gap of the force of electricity. Okay. So let's go ahead and get started with that. If we were to be able to have some kind of little magical hammer and we could smash apart a molecule into its parts, and then we'll find atoms, and if we break those apart, we're going to find that there's only 3 different things that make up normal matter. So this is normal matter. Okay, yes, there are more esoteric things that are out there, but the 3 pieces of normal matter are protons, electrons, and let me go over here. Protons, electrons, and neutrons. So particle name, proton, electron, and neutron. And of course, having taken, I'm sure, several semesters of chem at this point, you are well aware of this. So let's talk about their properties. I guess the first property I might as well mention is mass. They all do have mass. I'll put that mass in kilograms, which is our SI unit. You'll obviously find slightly different rounded off values of these, but these particles they're all the same. All protons are the same as all other protons, and so on and so forth. Here are the masses. This is 1.67 times 10 to the minus 27. 9.11 times 10 to the minus 31. And I want to point out that they are drastically different masses. The proton is about 2,000 times the mass of the electron. So if you've ever wondered, why is it that the electron orbits the proton and not vice versa, it's the same answer as why does the Earth orbit the sun and not vice versa. It's just a relative mass issue. Okay? Really, what you would more properly say is that they orbit around a common center of mass. And the common center of mass, if one particle is way bigger than the other, is basically starts to be indistinguishable from where the more heavy particle is. So that's a mass issue. And I specifically point this out because, as I'm just about to talk about, with electric charge, the proton and electron look like opposites, and so people get this perception that somehow they're exactly the same except for the sign of the charge, and that's not the case. Okay? They have very different masses. Okay? The neutron, it's approximately the mass of a proton, although there's lots of interesting physics in the approximately part as well. Okay? So it turns out one of the things in a weak nuclear force is that a proton can turn into a neutron or vice versa, and there's somewhere that the extra mass has to go. But we're going to not talk about the neutron very much at all. I'll bring it up later. The neutron's going to kind of get cut out at the moment and just kind of swept under the rug because it does not participate in the electric force. Right? So that's the very next thing that we have to discuss. So let's imagine we had access to each of these particles individually, and we could, in a controlled environment, start seeing how they interacted. So let's say we have a proton, or let's say we have an electron, and we have an electron. If you were to put an electron and an electron together, like that, you would find that they repel. Well, clearly that is not gravity, right? Because gravity is only attractive. So there must be some new phenomenon at work here, and that name given to that phenomenon by humans is called the electric force. So it's just a way to keep track of how these things really interact in nature. Likewise, if you take a proton and a proton, you will also find that those repel. So again, it's got to be something new. Notice there, just for symbolism, I've drawn them bigger to indicate they have more mass. And I can also put a proton next to an electron and see what happens, and they attract. Now, in this case, of course, you might say, couldn't that just be gravity? Well, it turns out that if you actually measure the force, it's way bigger than gravity. And so even though it's attractive, gravity can't be responsible for it entirely. In fact, there is an attractive force here. So that's what we find when we break apart things to their fundamental level and see how they interact. So let's compare this with gravity. With gravity, the property of the object, so I guess I'll say the intrinsic property, that we gave to objects to describe gravity was mass, right? And if you have this thing called mass, that means you interact with other things that have mass. And the interaction we talk about as being with the gravitational force, right? So basically, mass is what you have, force is what you do when you interact with others, okay? And of course, we only needed to say, do you have mass or don't you? Because if you have mass, you will attract other masses. It's only attractive. So basically, having mass means you belong to a club, and that club is attracting other masses. And we call that gravity, the force of gravity. So we need to similarly assign some kind of intrinsic property to these particles that will describe this new interaction, and we call that electrical charge. So we use the variable Q for it. Q is usually the variable. So if this is mass, this is electrical charge, okay? And if you have charge, you will interact with other charges, and that interaction we call the electric force. So if you have charge, that's how you react to other charges. Now, here we have the task of not only describing attraction, but also repulsion. So we have twice the possibilities that we need to describe. Gravity, we only need attraction. Now we have two different things that can happen. And so while there's only one kind of mass, we need to say there's two kinds of charge, the kind that a proton has and the kind that an electron has. And by the way, the neutron doesn't interact with either like this, so the neutron is basically out of the running at the moment. Okay? So there's one kind of mass, but there's two different kinds of charge, and we need some kind of nomenclature for that. The kind of charge that's on a proton, the kind of charge that's on an electron. So we could call them just A charge and B charge, just give them two names, but that's not going to be very computationally handy. So somebody at some point, I think it was Ben Franklin actually, thought, hey, we have two different kinds of charge, we have two mathematical signs, hey, that would be kind of a nice pairing. We can notate electrical charge with sign. Okay? It's just a human construct because there's two kinds of this thing and we have two signs. So we decide if mass is, of course, inherently positive because there's only one kind, we have both plus and minus charge. Now at this point, of course, this is an entirely human construct. You just basically flip a coin and decide which one gets assigned which. And that's exactly what Ben Franklin did. And it turns out, as we'll find out later, that there are reasons why he should have chosen the other way, but we're still stuck with the convention that he chose, which was pretty arbitrarily here, that the proton gets the plus kind and the electron gets the minus kind. So this is going to be our electrical charge. So there is a lot of advantages to using plus and minus. And one of the things that we do is that we realize if we have an equal number of both of those, then mathematically that would add up to could add up to 0. So what we do is we say that the proton and electron both have the same amount of charge. It's just one is of one type and one is the other. And that amount we call the elementary charge. Okay? And from here on out, E is going to stand not for electron, but elementary charge. It's called elementary because, of course, it's if you look at anything, that's kind of the end of the line, the building block. A moment mentioned in a second, that's not quite true, but in any case, we say that the proton has that amount of charge of the plus kind, and the electron has the amount of charge of the minus kind. So that's your fundamental building block of charge. Okay, those are the Legos of charge. All right. Now, at some point, the elementary charge was established, and we started using it. Then someone had to go figure out that you can split a proton into 3 pieces. You can actually break a neutron into 3 pieces as well. Does anyone know what those pieces are called? Quarks. They're called quarks. So it is possible to subdivide further from an elementary charge, but the principle still holds, right? The principle still holds that you can't just subdivide it willy-nilly. There are some fundamental building blocks that can be used. Probably if they discovered quarks before they set the elementary charge, the quarks would have gotten the E, okay? But at the current moment, or because of historical reasons, for a long, long time, it was thought that these were the building blocks that you couldn't get any smaller than, so that's why it got called elementary. And again, let me fill in the chart. Neutron does not participate in this at all, okay? So, one of the advantages of the plus and minus mathematically is that let's say you have 5 protons and you have 5 electrons. Well, that will naturally add to 0. So that would be a neutral atom, as we call it. Okay. So we call this neutral when the Q net of something is 0. So it would be a lot more awkward if we called it charge type A and charge type B, because then we'd have to remember that there's something special about 5 A's and 5 B's. Okay? But this very naturally mathematically comes out to be that if something has an equal number of both types of things, it's meaningful. It adds up to 0. Okay? And I guess I should mention that if I were to label these charges here with the benefit of hindsight, I would probably call this E minus and P plus. I don't want to use E in vain. E is going to be standing for elementary charge, so I don't want to use E for electron 2. I'll say E minus for electron and P plus. You might ask, so this is where the misconception again comes from, is that because they have equal and opposite charges, people think that they're carbon copies in every other way. You might ask, is there such a thing as a particle that has the same electric charge, or the same mass rather, as an electron, but of the positive kind? That does exist. Does anyone know what that's called? What's a charge that's exactly identical to an electron but has plus charge? Positron. So this sounds like obscure particle physics. Can anyone tell me what possible application that would have in your future career? A positron, something that's in a particle accelerator. What could that possible use have that have to medicine? Yeah, the P in PET scan. Okay, it's a positron. Right. There is, by the way, also a particle that is identical to a proton, but it's got a minus charge, so it's called an antiproton. You can even make antihydrogen by combining those 2 particles I mentioned. Not something you find around every day, but they exist, hence my statement over here. Let's just keep it to normal matter for the most part. Okay. All right, so that's how electric charge is measured. And that's where all electric charge on macroscopic objects is born, is by some imbalance of these. Okay? So if I go over here, I'll make myself a little number line. And this is going to be my net charge number line. And sitting right in the middle is 0, and we call that 0. This is something that's neutral. Things that are neutral, well, it could be just a neutron or a million neutrons. Something just completely doesn't participate in this whole idea. So a neutron or neutrons would be an example. But also it could be just some big object like yourself, where there's basically an equal number of protons and electrons. So unless you've just gone around and scuffed your feet along the carpet, chances are that you are a very large collection of molecules, atoms, and basically you have equal numbers of these things. Okay? So the way that something has charge is because there starts to be an imbalance. If you have one extra proton, you could have a charge of plus E. If you have two extra, you could have 2E. Notice these are like rungs on a ladder. You can't be in between. You can't just break up a charge willy-nilly because you're working with these small building blocks and that's the only thing you can do. You can either add or remove protons and electrons, but that's basically all you have. Anytime you're over on this side of the number line, the number of protons exceeds the number of electrons. That's why you have a net positive charge. How might you get that to occur? Well, one of the things you could, of course, do is add protons, but as we will find, it's much more easy to manipulate on the electron side. So probably what's happened is someone has removed electrons, okay? So it's much more likely that someone has removed electrons from a neutral object, and that's why it is now positively charged. So these are rungs on a ladder. As we say to be fancy, charge is quantized. You can't have any amount of charge you want. It's not a continuous variable. You can only cause charge by imbalancing protons and electrons, and those cannot be further subdivided. The best way to check if the amount of charge is allowed is to take the charge, divide by the elementary charge, and you'd better get an integer. Okay? If you get 1.5, how would you unbalance by 1.5 electrons or protons? You can't. All right? So a permissible amount of charge is an integer imbalance of elementary charges. Likewise over here, the first negative charge you can have is minus E, which is your one electron extra. Over here, the protons and the electrons are out of balance the other way. Next one you can have is minus 2E, minus 3E, okay? These are rungs on a ladder. You can't step in between. How would you cause this? Most likely, you are going to manipulate the electrons, so you're going to add extra electrons. We'll find it's a lot easier to manipulate the electrons, which are on the outside of the atoms, than to be messing with the protons in the nucleus. Okay? So these are the rungs of the ladder for electric charge. These are the only permissible values. But the one thing that I do want to mention is that we should zoom up from the very, very smallest atomic level up to everyday life. And we have a whole set of units that's designed for that. And that is the SI units, hopefully familiar from Physics 1. So SI units. Let me remind you what those are. Our fundamental building blocks were kilograms for mass, meters for length, seconds for time, and radians for angle. Those I introduced on the first day of Physics 1, and then we made all sorts of composite units, which are just combinations of these. Things that you might remember: a Newton for force, Joule for work and energy, Pascal for pressure, right? Those are just combinations of these. Well, we need a new unit. There is no way to express the unit of electrical charge, which is a completely new, separate thing in terms of these. So we're going to add to the list a Coulomb, capital C for short. That's the unit of electrical charge. And that will do it for Physics 2. These are the fundamental units necessary for Physics 2. We'll have composite units that include the Coulomb somewhere. You may have heard of some of them. volts, amps, ohms, things that we use in electricity. Okay? So that is not the complete list of SI units. I think there are, I can't remember, 7 or 8 fundamental building blocks. There's one for temperature, Kelvin, you've probably heard of that one. Number of moles, you've heard of Avogadro's number. But it's a fairly short list, and all other units are composites of these. And for those of you that may not remember or may not have used it last semester, there is available for you, as soon as I set it up, a units guide on Web of Science. So this is particularly helpful in Physics 1 because it lists what are the units, SI units of everything. What is the name of the unit? What is an abbreviation for in terms of these? What are other common weird non-SI units you might run into? So if you ever run into, what's a barn or a, I'm trying to think of other obscure unit, parsec, okay, you look up